Welcome everyone. So here we have another problem from Hippomathamus collection, this little cute guy there. Here we solve graduate level calculus and analysis questions right in front of your very eyes. So today we have a compact metric space X, and we have a self map F from X to X, which satisfies this distance condition. When I apply F to two pairs of points, the distance goes down strictly, of course, for X not equal to Y. Prove that F has a fixed point. So before beginning to solve this, let's see where this all comes from. So the usual fixed point problem you are presented in a course is where you have the C, which is less than 1. So there is a C less than 1, necessarily non-negative, where you have this condition with equality allowed. And then you prove that starting with any point, if you iterate by applying F again and again, you will in the limit approach some number which is a fixed point. So what is different here is that there is no such C. C is actually equal to 1. The compensation being that, well, you have strict inequality, but that is not the significant assumption here. The most important assumption here is that you have compact metric space. So compactness somehow compensates for losing the C, and you end up having a fixed point nonetheless. So for the solution, it's actually interesting that the following method will not work. If you try to actually show that this shows that there is in fact a C that you can plug into here, well, maybe because your set is compact and there's a maximum number you can put here, and that has to be less than 1, then I have bad news for you. It doesn't work. So I leave it as an exercise for you to find a compact space and such a map with this condition where you cannot plug in C less than 1, and this inequality still holds. So how do we go about the proof? Well, here's a quite interesting solution to this problem. And the idea is to define a function phi, which goes from metric space X to 0 plus infinity. So a non-negative function, real valued function. So how does this function act? If you give me a point in X, I look at X, I look at f of X, which is another point in X, and I look at their distance. So define such a function. What can we say about this function beyond the fact that it is non-negative all the time? So my claim is that phi is indeed continuous. Well, let's stick to this one. Why should phi be continuous? One way of doing that is just to compare phi x to phi of y, subtract them, and then wrestle with some triangle inequalities, and you will see that indeed it is 2 Lipschitz. However, there is the following proof as well. So what you do is you go from metric space X into metric space X times X, and then from that space you go back to real line. And how do these maps work? Well, the first I give you X, you take it to X and f of X. This is a continuous map. Given that each component is continuous, f is continuous, and X to X is the identity map, is definitely continuous. And the way you go from XX to R here is the distance map. So if I give you XY pairs, then you take it to distance of XY. So when you apply d to this x f x, it gives you distance x f of x. And d is continuous as well. If anything is continuous on a metric space, that is the distance function. It's the very object from which the topology on the metric space comes from. Okay, and so the final result is that my phi as a composition of these two continuous functions is also continuous. So that is one thing. If you don't like this proof, it's actually tricky. Go ahead with the straightforward phi x minus phi y. Okay, now I have a phi that is continuous, but it is continuous on a metric space, on a compact metric space. And we know what compactness means. So X is compact. So phi has a minimum. That means there is, so suppose phi of x naught is less than or equal to phi of x for every x in x. So that is x naught gives you the minimum value possible for phi. The claim part is that phi of x naught is actually 0. So that is the claim part. So how do you prove this part? The little proof of the claim is that suppose by contradiction phi of x naught is other than 0, then what do we know? We know that phi of x naught equals distance of x naught from f of x naught. That one is not 0. And that implies that x naught is some point other than f of x naught. Now we have this assumption, the main assumption on f, that if I have two different points, when I apply f to them, so let me apply my f to these distant points. So f applied to the other point as well, then the distance goes down. So this becomes less than distance of the points I started with before applying f to them. And this quantity is just phi of x naught. Now the point is that this quantity on the left is also a phi. This is phi of f of x naught. If you call this f of x naught as z, it's a point in x, then what we've seen is that phi of z is strictly less than phi of x naught. But how can that happen if x naught was the absolute minimum value for phi? So that's a contradiction. Therefore, phi of x naught is indeed 0. Now, the whole point of showing that f of x naught was 0 is the following. Conclusion of the proof is that, well, phi of x naught is 0, which implies by definition of phi, x naught f of x naught, this is probably already included in the above, this is 0. And that means when do you have distance of 2 points equal? Only if they are equal. So f of x naught equals f of x naught itself. And that means x naught is a fixed point to my f. And that's the end. And our hippo is happy. So below in the comments, if you come up with the counter example that I asked for, if you find that, commented. If you have problem understanding any part of this proof, comment that, and hope to see you again in some other problem in your future. Take care.